recording of this class has begun, so anything, that you say may or may not be picked up by this said microphone. So, yesterday we talked about what families on the periodic table were. And we said that families are elements that are where? Andrew?
Families are the columns in the periods on the rows.
Okay, so families are going to be elements that are in the same group, or on the periodic table we would look up and down the same column. Okay? So elements in the same column are in the same family. And we talked about yesterday that there is something that makes all of those elements similar. Do we remember what makes those elements similar from our discussion yesterday? Katerina, even though you weren't there, do you want to talk about it?
Valence electron?
Well, yes, although we didn't call it that yesterday, okay? Yesterday we talked about it in terms of their electron configurations, okay? We looked at the electron configurations of elements that were in the same family, and we found out that they are all similar in the fact that they all end the same way. That when we looked yesterday, we looked at 3 elements. We looked at lithium and sodium and potassium, and we saw that the ending of lithium's electron configuration was 2s1, and sodium's was 3s1, and potassium's was 4s1. So they are similar in the fact that their electron configurations end the same way. So, Katerina, today we put a name on that, and we call that ending electron configuration the valence electrons. So valence electrons are electrons in the highest occupied energy level of an atom. So valence electrons are electrons in the highest occupied energy level of an atom. And we said that there is a way on the periodic table that you can tell what the highest occupied energy level is. How is that? The energy level relates to what quantum number? The principal quantum number. And we said that the principal quantum number relates to what on the periodic table? What?
A number of rows.
Or what row it's in, right? That each row that element is in corresponds to another principal energy level, or moving one ring out on the periodic table. Okay? Here is a picture of chlorine, if I remember correctly. But chlorine, this picture of chlorine is written in a Bohr fashion, or it's a Bohr model of chlorine. Why is it a Bohr model of chlorine? Why is that a Bohr model? Maura, go ahead.
So, because it's in like orbits around the nucleus.
Right, that those electrons are in orbits, right? These 2 electrons are here, these 2 electrons are here, these electrons are here, there's 8, these 7 electrons are here, right? On the test, I use this as a test question, right? One of these spots can't have electrons, right? Which spot can't have electrons? B, right? According to Bohr, right? Because that's not on a ring, right? Now, for our discussion here, which one of these electrons, A, C, or D, is going to be a valence electron? Andrew?
C.
Nope. A is going to be a valence electron, because where is A? Which ring is A on? The highest ring. So when we're talking about valence electrons, right, we're talking about electrons that are where in an atom? In relation? The highest ring, or Christine, in relation to the nucleus, close or far from the nucleus? As far as that atom will let us get from the nucleus, right?
Doesn't occupied mean most abundant?
No, occupied just means that there is something there. Okay?
But C has most electrons.
That's true, but that doesn't mean it's the highest occupied level. Okay? The highest level that is actually occupied is that outer ring. Okay? So Andrew, if we look at those pictures, let me pull this up. If we look at the pictures, where is it? Nope, not there. I don't remember what I called this. There it is. Too far. This will look good on the recording. Stand by.
Can you put some elevator music?
Why did you just pause it?
No, I said, can you put some
I could have just paused it, couldn't I?
Okay.
That wouldn't give it the authentic feel, you know, like you were really here, you know. So, all right. So down on the bottom, and you see that I have mine are cool colored gold. Yours don't get colored gold, sorry. But on the bottom in the middle, that's the Bohr model of chlorine that we were just looking at, right? So the highest energy level here is the third energy level. And if we look at chlorine, there are 7 electrons in that energy level, okay? Up here for sodium, right? The highest level that has electrons in it is also the third level, okay? But it only has how many electrons in the third level? Just 1, right? Because, you know, so Andrew, it's not exactly how many there are, it's which area or which ring has which is the farthest ring that actually has electrons in it.
Okay, I understand now.
Okay. All right, good there? Okay. So, if we look, right, the top 3 are Bohr models of the elements that you wrote electron configurations for yesterday, right? And we said that the thing that makes them all similar is their electron configurations, especially the ending of their electron configurations. So now we see that if we look at their quote-unquote valence electrons, right, how many valence electrons does lithium have? 1. How many valence electrons does sodium have? 1. How many valence electrons does potassium have? 1, right? They're in the same family, they have the similar electron configurations, they have the same number of valence electrons. That's going to be super, super important when we start talking about bonding in a couple chapters from now, okay? Because these valence electrons are important to bonding, or what we refer to as chemical reactions. And we will spend a whole unit talking about that. But for our discussion today, what that means is that if one element in a family forms a certain kind of compound with another element, pretty much any other element that's in that family will form the same kind of compound because they have the same number of valence electrons. This part here about getting to 8, that's going to be important later on, so I won't introduce that idea. 8 is the magic number. That's what atoms are looking for as far as the number of valence electrons, because that puts them in a lower energy state. We discussed in the previous unit that atoms have the same number of protons and electrons. That's true. But that doesn't always mean they're stable with the same number of protons and electrons. Sometimes it is more advantageous for an atom to have more electrons than protons. Sometimes it is more advantageous to have more protons than electrons. It comes down to an energy thing, and we will talk more about that in the bonding chapter. Okay? But if we look here at this table is similar to a list that I showed you yesterday, that if we look at the alkali metals and their electron configurations, right, that we said that each of their electron configurations in the alkali metals ends in the s1 orbital, or in the s orbital with 1 electron in that s orbital. We said the n corresponded to whatever row they were in. And we see that there's a pattern there, right? This is S1, these are S2, and the pattern continues. But more importantly, all of the elements in this column have an electron configuration that ends with S1. It's either 2S1 or 3S1 or 4S1, but it's still S1. And that means that elements in the same group have similar properties because they have the same number of valence electrons. Elements in the same group have similar properties because they have the same number of valence electrons. Yes, Adrian?
These electrons play a key role in?
Chemical bonding or chemical reactions. We will spend a whole unit talking about that. Not the next unit, but the unit after that. All right, good there with this idea of valence electrons? So now, let's start talking about how these valence electrons influence the properties of the groups of elements on the periodic table. Okay? So, first family that we're going to talk about is called the alkali metals. Okay? Over on the board, over on the sideboard, the first period class, they made us a little three-dimensional periodic table. It's not complete. There's some things missing because some people didn't complete their assignment that they were supposed to, and then other times the teacher forgot to assign one of the families on the periodic table, so there's space there. But we can use it as some reference. Okay. So alkali metals, like it says up on the board, are found in group 1, meaning we're going to find them where on the periodic table? Left or right? Far left, right? It's the first yellow column over there on the far left, okay? We refer to that group as the alkali metals, okay? Group 1, sometimes, I mentioned to you guys yesterday that there are different ways that we can classify the different columns on the periodic table. So sometimes you will see it referred to as group 1A, just depending on what classification system we're talking about, okay? So, these alkali metals, first, even though they are metals, they are very soft. If you had a pure sample of any one of those metals, you could cut it with a knife. Okay? Yes, it's a metal, but not necessarily a metal in the way we think of it. Okay? These metals are very shiny, but you don't find them very often by themselves because they only have one valence electron. Every element in group 1 has one valence electron. That makes it very reactive. You will almost never find sodium or potassium or lithium out there in nature by itself. It is almost always a part of a compound where it is joined with another atom because they are so reactive. You can't go and dig up sodium out of the ground. It doesn't exist that way. It exists as part of a compound joined together with other atoms. Go ahead, Andrew.
What would happen, but are there pure sodium substances in existence? Can it be
We can make it in a laboratory, yes, but the first chance it gets to form a compound with something else, it will do so.
Like,
Okay.
so it was placed on a wood table to try to compound with the wood.
Say again?
So if you place the pure sodium substance on a wooden table, you try to compound with
Yeah, and mostly though, not so much with wood, it reacts with the oxygen or the water that is in air. So even if you just like put it on a table that with something like a piece of rock or whatever that's very supposed to be like, you
It'll
know,
just dissolve immediately.
it might not dissolve. It actually like starts forming a reaction, which looks kind of like a little fire or an explosion. We'll talk about that more, about
Yeah,
why it looks
I'm
that
gonna
way.
see a video of that.
Oh, not today, but yes, she will eventually. So.
Maybe that look awesome.
What?
That look awesome.
It is pretty awesome. So I have to say, okay. That also means that if you do have a pure sample of this, okay, we have to store it under special conditions because we can't just leave it in the cabinet because it will start reacting with the oxygen and the water that's in the air and form a compound. Catherine, go ahead.
What's the significance of getting 8 valence electrons?
That is a low energy state, okay? We'll talk way more about that when we talk about chemical bonding, but remember, Catherine, we said that in nature, things tend towards lower energy states, right? That's why electrons exist as close to the nucleus as they can while still repelling all the other electrons, because that is a lower energy state. 8 valence electrons is a low energy state. It's not so much important that an atom has a balance between protons and electrons. It's more that they need 8 valence electrons. So even if that means they might end up with more electrons than protons, that's actually more stable for them than having a balance of protons and electrons. Most elements are like that. Most elements do not exist naturally as just themselves, because they trade electrons with other atoms in order to get to a lower energy state. Okay? We will talk way more about that when we talk about bonding. So if you don't quite understand it now, don't worry. I wanted to introduce the idea right now so that we can come back to it again and be like, hey, remember when I told you about 8 valence electrons? Here's how it works. Okay? Trey, go ahead.
For number 3, did you mean alkaline earth metals? It says alkali again. No, like on our sheet.
Oh, alkali metals and alkali earth metals are 2 different things. Sometimes we'll refer to them as alkaline earth metals, which I have here too.
Yeah.
Yes, Andrew.
So the alkaline metals are lithium, sodium, potassium,
Rubidium,
rubidium.
cesium, francium.
Of all of those, which is the easiest to find in its pure substance?
Lithium.
And okay, so if I put lithium on a table, it'll react like the sodium.
It won't burst into flames, but it will start reacting. So.
Okay.
All right. Next, group 2. Group 2 we refer to as the alkaline earth metals or the alkali earth metals, depending on what periodic table you talk about. Okay. So group 2, or sometimes referred to as group 2A, right? So it's the second column. Up on the 3-dimensional periodic table on the board, those are in blue. Okay. That column not completed because the people that were assigned that column did not finish all the things that they were supposed to. Okay. But I know. So, alkaline earth metals, they are still metals, okay, meaning that they are reactive, but they're not quite as reactive as your alkaline metals. They are harder, they are denser, and they are stronger than your alkaline metals, but still, we won't necessarily find them by themselves. You don't just go out and dig calcium out of the ground, okay, or
That would be-
magnesium. Can't do it. Okay?
How would these alkaline metals look like like in a pure substance form?
They're generally pretty shiny, okay, especially the alkali metals, but the first chance they get to react with water or air, they lose that shininess and become more of like a dull color because that's the compound that they
So
form.
will you show us pictures of these elements in the pure
You could look them
substance?
up. Go look them up.
I know, but what do I look up like sodium alkaline metal?
Type in pure sodium into Google and go to Google Images and you'll find it there.
Pure sodium.
Alright, so that's alkaline earth metals. Good there? Alright, we're going to make a big jump next. And we're going to go to group 17, which we refer to as the halogens. Okay? Periodic table on the wall, group 17 is a yellow column, way over on the right-hand side. Okay?
And
It's supposed to be 17A.
No. It's group 17 if you just number them from left to right, okay? But, Catherine, we said that sometimes there are other ways that we can distinguish those columns or label those columns. Sometimes this is referred to as group 7A, okay? So it's group 17 if you just go left to right, but sometimes you'll see it referred to as group 7A, okay? All right, first, metals or nonmetals? Non-metals, right? So we're going to have different properties than our alkali metals, okay? First being that there is a large variation among your halogens as far as what they look like. Some halogens are gases at room temperature. One is a liquid. Some are solids at room temperature. So there's a large variation among even the properties of the elements in the same family. But one thing that they do have in common is that they are very reactive because when you draw Bohr models, or if you look at electron configurations for these elements, they have 7 valence electrons. And the pictures that were on the front of your outline, the Bohr models that were on the front of your outline, the ones at the bottom, these are all halogens. They're all group 17. And if you look at their outer ring, they all have 7 valence electrons. So they're pretty close to having 8. That's why they are very reactive. They are looking to gain that last electron that makes them stable. Okay? But right next to these halogens in group 18 is a group of elements we would call the noble gases, or the inert gases. If you look at electron configurations or valence electron Bohr models, okay, noble gases already have 8 valence electrons. 8 valence electrons makes them stable without combining with other atoms. Therefore, they have a very low reactivity. They don't form compounds with other atoms. We won't find them in nature joined together with other stuff. We find them by themselves because they already have 8 valence electrons. Okay? So they're good for storing stuff like sodium or potassium. If you need to have something that doesn't react with other stuff, you can put them in an environment, a room or a box or something filled with a noble gas, because that noble gas won't react with whatever else is there. Okay? Good there? One of the reasons why, you guys know the story of the Hindenburg,
Yeah.
the blimp that caught on fire, like 1937 or something like that. Well, maybe it's earlier than that, 1917, maybe something like that. Anyway. You've seen, come on, you've never seen the picture?
No.
Come on, big blimp on fire.
It's a gigantic blimp on fire that
No.
exploded.
Come on, Laura. All right.
It's just like,
What?
no.
On my
Laura, you really have seen the picture. You just want me to stop class.
No, I seriously haven't.
They did it on Mythbusters.
So why does the can't
It's
flow?
really funny. I've never seen this picture.
This picture right here, Maura?
I've never seen that.
Come on. I've never seen that picture.
No.
Have you never seen that?
I've never
I
seen
don't know. I guess my parents just didn't show me burning blimps when I was.
I mean, it's not like something you show your kids. It's just like famous, it's famous like.
You're not just like.
So this one
This
actually.
could happen to you one day.
So this one was artificially colored. They didn't have color photography back then.
So
But,
how did everyone find out about this but me?
I
You're
don't
just.
We have a secret cult. Just don't let Maura in.
All right, but
I hope this is about you.
the Hindenburg. Okay. The Hindenburg was one of the last blimps that was filled with hydrogen, because hydrogen doesn't have 8 valence electrons. Therefore, it is reactive, and if it is given the opportunity, like a spark or something like that, this will happen. Okay? But if we would fill that blimp with something like helium, right? Helium is stable. It already has a full valence shell. We refer to it as full valence shell. Okay? And therefore, it doesn't react with other stuff. That's why we can fill party balloons with helium, right? And you can breathe it in, okay? And it doesn't really hurt you. You know what I'm saying? Because it doesn't react with anything in your body. Okay? Now, that doesn't mean you can breathe in as much helium as you want to, right? If you breathe in too much, well, even besides that, right?
Could your voice actually be stuck like that forever?
No, it's not so much that, but if you breathe, Maura, if you breathe in so much helium that helium starts taking the place of like regular air in your lungs, that's a problem. You know what I'm saying? Do you understand why it's a problem?
God.
Helium, man.
Actually, first you'll probably just pass out. You won't die right away, but.
Right, but eventually.
If we fill this whole room filled with helium,
We die.
and you breathe, we got a problem, right? Because, we need the oxygen. So. All right, hydrogen. Atomic number 1. Hydrogen is unlike pretty much any other element on the periodic table because It only has one proton and it only has one electron. So all those things about, where do electrons settle, what orbit are they in, blah, 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 doesn't really apply to hydrogen because it's only got one electron to worry about, right? But we always see it on the periodic table at the top of group 1, although it's not really like the alkali metals, okay? Alkali metals behave a certain way. Hydrogen doesn't exactly behave that way. It is reactive, but not necessarily in the way that alkali metals are. So even though it's at the top of group 1, that doesn't necessarily mean it's an alkali metal. Okay? And then, wrapping it up, yesterday we talked about transition elements or transition metals, right? They're metals, not as reactive as group 1 or 2. Okay? They are harder, more dense, higher melting points than those elements in group 1 or group 2 for that matter, except for mercury. You may be aware mercury is a liquid at room temperature, right? The reason why these are a little different in reactivity than our alkali metals or alkali earth metals is because they are starting to fill d orbitals. The screen is in the way.
Oh.
It's in the way of the screen. So.
What is HG? I'm looking
Mercury.
really bad.
Mercury.
I see.
And mercury is a metal, mercury is a liquid at room temperature. Okay. So if you look at the electron configurations for these elements, they all end in the D level. So sometimes we refer to this as the D block of the periodic table. One thing that you will find out, a little bit more so in chemistry, is that when we look at the actual electron configurations for these elements, they don't all follow that nice, neat pattern that I introduced to you in the previous unit. They don't exactly go from the bottom of the chart to the top of the chart in the order that the orbitals appear on that chart. Because once we start getting d orbitals, you may remember from the chart that there isn't much difference maybe between a 4s and a 3d. And if you start throwing in like 6ds and 5s's and things like that, we'll find that those elements don't exactly follow the pattern. There are some irregularities in their electron configurations. So predicting their reactivity or how they behave sometimes is difficult to do. Okay? And then the last ones, the two down at the very, very bottom. Okay?
What about many irregularities in the D block?
Say again?
It says many irregularities in the D block.
Irregularities? Okay. Oh, many irregularities in electron configurations. Okay. Palladium is one example of that. Okay. But there are lots in there. So I said that it doesn't always follow that nice orderly filling sequence that I introduced to you in the last chapter. Okay. Good? Last, the two rows down at the bottom that we sometimes refer to as the F block, because if you look at their electron configurations, they will be filling up F orbitals. Okay? The top row we refer to as the lanthanides or the lanthanoids, depending on what you call them. Okay? Depending on what book you read and stuff like that. They are shiny and they are very reactive. Okay? They're just like some other metals. But the bottom row of the periodic table we refer to as the actinides. Most of those elements don't even exist naturally in the world. We create them artificially, and they are radioactive. That means that the nucleus falls apart, right? Too many protons, too much repulsion, and they give off energy. We create them artificially to then use them in situations where we need that radiation, like X-rays or radiation treatment for cancer patients or stuff like that. Okay?
So uranium is a main name?
Uranium is the last naturally found one. Okay, 92, or Andrew, 92, that's the biggest nucleus that we find naturally in the universe. Anything past that is made artificially in the
So
laboratory.
like Einsteinium.
Einsteinium, Neptunium.
America.
Those are things. So if I make a new one,
Oh, that's
I was
We talked about this yesterday, Katerina. That if you get,
the high cows of chemistry.
if you discover a new element, you get to pick a name, but that doesn't necessarily mean that the name is that's gonna be the name.
It is
You have to submit it to approval.
Is
The
mendelevium
high council of chemistry that we talked about yesterday.
Wait, Christine, did you just forget to color these?
No,
So I have a
because they
question.
didn't exist, and I said I don't care
If
about
I'm
the
Maybe I
There's
don't
one